Check it out now, y'all.
NanoHub U, online instruction.
Hi again. We're back, and we're discussing the third lecture in this series of lectures that introduce you to some of the fundamental concepts of probability. And in particular, this lecture, we want to focus on what happens as you let the number of particles or the number of trials in a particular problem get very large. And it turns out the consequences of this are pretty far-reaching, and I like to try to describe the situation as best I can. So the underlying theme of this lecture is going to be when you deal with small numbers of particles or small numbers of possibilities, you really have a random chance of achieving any possible outcome. But as you let the number of particles increase, or the number of chances increase, you go from this random chance to virtual certainty. And I like to try to illustrate that in a very simple way by just asking you to think about keeping track of all possible outcomes of flipping a coin n times, okay? So if we flip a coin 2 times, 3 times, 4 times, 5 times, what happens to the outcome of those events? So let's start discussing it in a very simple way. If n represents the number of times we flip a coin, right, and we just flip a coin once, right, the possible outcomes of that experiment is either heads or tails. So there's 2 possible outcomes, and each outcome has a 50-50 chance of occurring, right? If we flip the same coin twice, right, now the possible outcomes start to increase, right, because we could flip it twice and we would get 2 heads, we could get 2 tails, or we could get 1 tail and 1 head, right? And this middle possibility can occur in 2 ways, because the tail could occur first and then the head, or the head could occur first and then the tail. So this middle possibility has got a degeneracy or weight of 2. So we can consider doing this as n increases, right? And we can start to ask, what are the possible outcomes of these n coin flips? So I think it's useful to start a plot to try to illustrate the main idea of the lecture. And so I've done a plot for 1 flip, for 4 flips, for 8 flips, and then for 16 flips, just to illustrate the idea. So if I flip the coin once, there's a 50% probability of heads, 50% probability of tails, right? So there's just 2 outcomes. If I start to flip the coin 4 times, then if I plot the number of heads that I can achieve versus the number of coin flips, right, what I find is there starts to be a distribution of possible outcomes. So the most likely outcome of 4 coin flips is 2 heads and 2 tails, right? And that occurs with a probability of about 37%. If I then consider the case of 8 flips of a coin, right, I get now 8 different outcomes, and the likelihood that I get 4 heads and 4 tails is still the greatest outcome. It's got the highest probability. But what you can start to see is you can start to see now that I've got a distribution of outcomes that start to result. If I flip the coin 16 times, right, now the most likely outcome is 8 heads and 8 tails, but clearly now I've got a very well-defined distribution where the possibility that I get, let's say, 0 heads, or the possibility that I get 16 heads is essentially 0, right? The most likely outcome, again, is 8 heads and 8 tails. This plot here can be generated by considering all the possible outcomes which I can enumerate in a table. And so I've gone through the effort to make this table because I had to make this table in order to create this plot. So what you have to be able to do is you have to be able to list all possible outcomes of 16 flips of a coin. And in this case, it's pretty easy to enumerate those possible outcomes. And then you have to figure out the number of ways each of these outcomes could occur. And the number of ways each of these outcomes could occur is then given by this fundamental formula that says you've got n outcomes and you choose n possibilities. So I just work out the case of 3 heads and 13 tails here on the side, just so you can convince yourself that you can calculate these values for any possible outcome, right? So these number of ways that any outcome can occur, this is referred to as the weight or the multiplicity or the degeneracy of any of these possible states that might result. And you can see that this multiplicity, right, plays a critical role in determining the probability, because if you've got 560 ways of achieving this particular result, then the probability of achieving 3 heads and 13 tails is going to be the ratio of 560 divided by 65,536. And that's how I got all these numbers to put in this particular plot. Okay? So that's the main idea. That's the idea that we're trying to discuss. What is the certainty that you would obtain, let's say, 8 heads and 8 tails? So this is the probability for 16 flip. This is the probability distribution for 16 flips of a coin, and I'm asking now for some sort of a quantitative measure of the likelihood that I'll get these 8 tails and 8 heads, right? Well, about 20% of the time I'll achieve that outcome, but that's far from being certain. And the reason it's far from being certain is that this distribution curve has a finite width to it. And so let's designate the width of this curve as some number. Let's call it 2 sigma just to give it a symbol. And what we can do is we can identify 2 sigma as, for instance, equal to a spread of 4. So this goes from 6 heads to 10 heads. That spans this arrow of 2 sigma. And what I can then start to calculate is I can start to calculate the ratio of 2 sigma to the mean, right? And the smaller this number becomes, right? In other words, as 2 sigma over mu gets smaller and smaller, then the probability of achieving the mean increases. So for this particular case, 2 sigma is 4, the mean is equal to 8, right? So the ratio of 2 sigma over mu is equal to 0.5. And that just basically means that there's a significant spread around this mean value. So the mean value is by no means well defined for this system of, let's say, 16 flips of a coin. It's really interesting to ask what happens as the number of flips increases. And you can do this calculation in a pretty straightforward way. The mean number of heads is always going to be equal to 1/2 the number of flips. So as n gets larger and larger, the mean value stays fixed at n by 2. But what you can show is you can show that this width of the distribution goes as the square root of n, right? And so if you take the ratio of 2 sigma over mu, right, and you let n get very large, what you find is that this ratio of 2 sigma over mu goes to 0. And that just simply means that the width of this distribution pinches in, right? It gets narrower and narrower. It's always centered about n by 2, but it gets narrower and narrower as the number of flips becomes larger. And that just simply means that the narrower this distribution curve gets, the higher probability you're going to have of getting the mean value if you flip the coin n number of times, right? And the mean value is half heads and half tails. So what you end up with is, for low numbers of flips, you've got a probability distribution curve. There's a certain probability that you're going to achieve n by 2 heads and n by 2 tails. But as n gets very, very large, right, the width of that distribution gets very narrow, and the outcome becomes almost a virtual lock. It becomes almost a certainty. I like to try to illustrate that by just making a plot of this ratio of 2 sigma over mu as a function of the number of flips. So here I'm considering huge range in the number of flips. I'm going from 100 all the way up to 10 to the 14th. And what you can see is that when the number of flips is small, let's say 128 or 256 flips, this ratio of 2 sigma over mu is a number that's close to unity. But as the number of flips gets very large, right, the ratio of 2 sigma over mu gets very small. And basically what's happening is you're going from random chance down here, right? So this is the regime of random chance where the statistics of head up, flipping a coin and getting heads up or heads down, that's equal to essentially 1/2, right? Where when you start to flip, let's say 10 to the 14th coins, right, the probability that you get 50% heads up and 50% heads down becomes very, very certain, because the width, right, the ratio of 2 sigma over mu gets very small. So this is virtually certain event in this case, right? You're virtually guaranteed that you're going to get 50% heads, 50% tails. Where down here, your chances of getting 50% heads and 50% tails is governed by the random flip of the coin. So this is an important revelation, right, that Boltzmann was particularly influential in pointing out. And it's certainly a feature that we're going to rely on as we discuss these n particles that are grouped together to form a system. What we're going to do is we're going to start to apply these statistical ideas now to some physical systems. And the first physical system we're going to consider is a classical gas of atoms. This has nothing to do with quantum mechanics. It's more of a reminder of the ideal gas law and what the underpinnings of this ideal gas law are. And what we're going to do is we're going to talk about the Maxwell distribution, Boltzmann distribution function. This Maxwell-Boltzmann distribution function applies to distinguishable particles, and we're going to use the ideal gas as the main topic of conversation in this discussion. We're going to then come back and we're going to apply the same line of argument to fermions and bosons, and we're going to find out what statistics are required to describe collections of spin 1/2 particles, electrons, and which statistics are required to describe bosons, which have an integer spin associated with them. So that'll come back. We'll be discussing those ideas in later lectures. Throughout the whole discussion, this idea of a density of states and a distribution function are going to be very important, and we'll try to bring out those ideas as we go along. So to begin with, by way of review, I'm assuming that most of you have heard about classical gas or an ideal gas. An ideal gas is governed by this very famous equation that says the pressure times the volume is equal to the number of moles N in the gas times some constant R times the absolute temperature T measured in degrees Kelvin. You can go to a website, for instance, and you can check out an ideal gas simulator. This is a nice website that I found. It allows you to change the number of particles in a container. It allows you to change the volume of the container. That changes the pressure, and also you can adjust the pressure by pumping more particles into a volume, and it allows you to appreciate for a small number of particles what this PV equals nRT is all about. So if you have time, please check that out. It's kind of a useful simulator. What I'd just like to do is I'd like to try to illustrate some of the microscopic physics and the assumptions underlying this ideal gas. The ideal gas is, of course, a concept that comes very close to mimicking the behavior of many, many gases, and it's kind of useful to understand what the microscopic physics is that underlies this PV equals nRT. What the standard assumptions in the ideal gas law contain are listed in this slide. We assume that the gas is made up of a large number of molecules or atoms. We assume that all the atoms and molecules are identical and that they are distinguishable, so they are classical particles. These are not quantum. This is not a quantum gas. This is a classical gas. We assume that the size of the individual molecules is very small compared to the average separation between two atoms or molecules. So the diameter of each atom or molecule is going to be small compared to the interparticle separation. Turns out that's a critical assumption, and that's very restrictive, it turns out. We assume that the molecules and atoms, as they move around inside of a container, those atoms and molecules obey Newton's laws of motion. We assume that the molecules or atoms do not interact with each other. So as they collide with each other or with walls of the container, we assume that there's no net interaction. That also is a very restrictive assumption, and it limits, it turns out that's one of the approximations that limits the applicability of the ideal gas law. We also assume that the collisions between the molecules and the container of the walls are all elastic, so that there's no energy lost in each collision. And lastly, we're assuming that the motion of the molecules is entirely random. So these 7 assumptions all feed into this very simplistic simulation that can be found at this particular website. And so it's kind of useful to at least try to enumerate what those assumptions are. Historically, of course, the ideal gas law has been known for a long time. In fact, there's a long history behind this. Historically, I think the problem starts out with Boyle in 1662. This is about the same time Newton was active in England. The ideas were picked up again by Charles in 1787. And then again by Gay-Lussac in 1802. And what they basically showed was through a sequence of very systematic experiments that the pressure of a gas times the volume of the gas is proportional to the absolute temperature T of the gas. And this is just a proportionality constant, or proportionality relationship at this point in time. It was not until the 1830s that Clapeyron actually came along and turned this proportionality into an equation. What he said was that the pressure times the volume is going to be equal to n, the number of gas atoms or molecules contained in that volume V, times some constant k sub b, which has to be inserted in order to convert temperature in Kelvin into the product of a pressure times a volume, which turns out to be in joules. So this constant k sub b is basically a unit converter, and if you count the number of gas atoms, capital N, then you write the ideal gas law in terms of Boltzmann's constant k sub b, which we now know has this value down here. If you come from a chemistry persuasion, then you tend to emphasize the number of moles in a gas. The number of moles are represented by small n. Because the units on the right-hand side of this equation are different, you have to come up with a different proportionality constant. That proportionality constant is capital R, and capital R is it's known as the universal gas constant. It's 8.3 joules per Kelvin. So I guess the point to emphasize is these are empirical rules, right? These are empirical laws that work very well for most gases. And what we're trying to do is we're trying to develop a microscopic understanding of what underlies this ideal gas law. So That's what we're going to address in the next lecture. We're going to very quickly review the kinetic theory of an ideal gas, and we're going to show you how, by tracking the motion of individual gas molecules, you can recover this very famous ideal gas law from a microscopic underpinning. So come on back and listen to that lecture. It'll be mostly review, but we'll be able to derive this ideal gas law by considering the motion of the individual atoms and molecules. So thanks a lot, and we'll see you at the next week's worth of lectures.